I'm P. Mabu Hussain, Assistant Professor of EEE in Institute of Aeronautical Engineering. So today in this video, we are going to discuss about the inductance of three-phase asymmetrical line with a transposition. So by the end of this lecture, the students will be able to explain the what is transposition of conductors and develop the expressions for determining the inductance for a three-phase asymmetrical line with the transposition. So before going to that, let us recall the last class. What is the content we have discussed? The first one is the recall the symmetrical line and its inductance value. So what is symmetrical line is nothing but if you take a three-phase transmission line, so in which you are having the three phases. Now if you observe the distance between any two conductors, that will be the same here. Right, the distance between any two conductors will be the same in a three-phase line. In such a case, the system is said to be a symmetrical three-phase line. Right, the inductance of such type of lines will be LA is equal to lambda A by IA. So whose value is 2 into 10 power minus 7 ln D by R dash Henries per meter. Right. So for a three-phase symmetrical line, the inductance in each phase will be the same. So LA will be equal to LB will be equal to LC. So which will be equal to 2 into 10 to the power of minus 7 ln D by R dash. So which is in Henries per meter. Now in similar way, if you observe the asymmetrical line, so in which if you observe the distance between any two conductors, that is not same. So D12 is the distance between A and B conductors, and D23 is the distance between B and C conductors. D31 is the distance between C and A conductors. Now this D12 is not equal to D23 is not equal to D31. Right. So if you observe the distance between any two conductors, these values are not same. In some cases, 2 may be the same. D12 may be equal to D23, but it will not be equal to D31. Right. In such a case also, you can call the transmission line to be a three-phase asymmetrical line. Now if you determine the inductance for these three-phase asymmetrical lines, the inductances for each phase will be different. Right. The value of inductance for phase A, which is LA, will be equal to 2 into 10 power minus 7 ln 1 by R dash plus A square into ln 1 by DAB plus A into ln 1 by DCA. So if you observe the inductance for phase B, LB is equal to 2 into 10 power minus 7 ln 1 by R dash plus A into ln 1 by DAB plus A square into ln 1 by DBC. Similarly, if you calculate the inductance for phase C, the LC value is 2 into 10 power minus 7 ln 1 by R dash plus A square into ln 1 by DCA plus A into ln 1 by DBC. Right, the derivation for all these three equations, so we were discussed in the previous video. Right, once you go through the previous video, so then you will get the derivation for this equation on how you can derive these equations. Right, so these are the inductances for a three-phase asymmetrical line. So in which if you observe the distance between any two conductors, it will be not same. Right. So now from these equations, you can say that the value of inductance LA, LB and LC, all these values depends upon the operator A here. So what do you mean by the operator A? So the value of operator A is 1 at an angle 120 degrees. Right. So this can be written as E or J 120 degrees. So which can be equal to minus 1 by 2 plus J root 3 by 2. So this is the value of A. Right. Now, so if you observe these three equations, each equation depends upon the operator A here. Right. So the value of inductance for an asymmetrical transmission line will be depends upon the operator A, whose value is a complex number. So the value of inductance is also here in a three-phase asymmetrical line will be complex values only. Right. And also the value of inductance, if you observe, so these are not equal. Right. So the inductance of an asymmetrical three-phase transmission line for each phase is not same. But in case of symmetrical line, so the inductance will be same. Okay. So now, so when inductances are not same, what will happen? So suppose if you take a three-phase line, So 3-phase line, this is the sending end and this is the receiving end, right? So you will supply a balanced 3-phase supply here at the sending end, right? If you supply a 3-phase balanced supply from the sending end, now when it comes to the receiving end, so then you will get a unbalanced voltages, unbalanced 3-phase voltages and currents you will get. So why? Because here for a asymmetrical transmission line, the inductances in each phase will be different. When the inductance is in each phase is different, the voltage drops across each phase will be different. So the voltage what you are getting here at the receiving end in each phase will be different, right? Which is nothing but unbalanced voltages will be you are getting at the receiving end. Okay, this is the main disadvantage you are having. So when you use the asymmetrical 3-phase lines, right? So now how you can overcome this, right? How you can overcome this unbalanced 3-phase voltages which you are receiving at the receiving end, right? So this can be done by using the transposition of conductors. Okay, so by transposition of conductors, you can get the average inductance for each phase will be the same, so that you will get the balanced receiving end voltage at the receiving end. Okay, so then what do you mean by transposition of line conductors? So transposition of conductors is nothing but it is the exchanging the position of conductors in a 3-phase system along the transmission distance in such a way that the conductor will occupy the original position of every other conductor over a equal distance. Okay, so in what do you mean by transposition of line conductors? So transposition of conductors is nothing but simply the exchanging the position of conductors in a 3-phase system such that each conductor will occupy the original position of every other conductor also in a equal distance. Suppose let us take a transmission line which is having a distance of 1 meter, let us assume, okay, or let it be L meters. Okay, so the transmission line is having L meters. Now this transmission line is divided into 3 sections. Okay, so 3 sections we are dividing. So each length will be 1 by 3, 1 by 3, 1 by 3. Okay, so now initially at L is equal to 0. So if you observe the position of 3 phases, here 3 phases are A phase, B phase, C phase. Now if you observe the position of 3 phases, let us assume that phase A will be in position 1, phase B will be in position 2 and phase C will be in position 3 here. Now after some distance 1 by L by 3 here, so L by 3 distance, now the position of this A will be changing to position number 2. Okay, so in the first section conductor A or phase A is in first position, and in the second L by 3 distance the conductor A is in position 2, and if you observe the last third section, so then conductor A will be in position number 3 here. Okay, similarly, right, so if you observe the position of conductor B here, initially in the first section it is in position number 2, so then in the second section it is coming to position number 3, so then in the third section it is coming to position number 1 here. Okay, so similarly if you observe the phase C, so the phase C is initially at the third position, so then after 1/3 distance it is going to position number 1, so then further 1/3 length it is going to the position number 2, right? So such that the conductors will be arranged. Okay, so this is called the transposition of line conductor, right? If you observe the transposition of line conductors here, so each phase of conductor is occupying the original position of each and every other conductor. So that means if you take any phase which is starting at the initial position, that will occupy the other positions also at equal intervals. Okay, if you have the total length of L here, right? So then L by 3, L by 3, L by 3, right? You will be divided into 3 halves here, right? Now the exchanging of conductors will take place every L by 3 distance, right? So this is called the transposition of conductor, right? When you use this type of configuration for asymmetrical lines, in such a case, you will get the average inductance to be same in each phase, so that you will get the same voltage drop across the line, so that at the receiving end you will get the balanced voltages. Okay, so here transposition is done at equal distance always. So in the figure here, what we discussed, so the distance, equal distance is 1 by 3 of total length of the transmission line, right? Here we are taking 1 by 3 as the reference, right? So but you can take any distance, right? So that must be equal, right? Your total length of the transmission line will be divided into equal distances, right? At each transposition point, you have to transpose your conductors. Okay, so here and here, so there are 2 points here. So at this place, the conductors are changing their position, and here also the conductors are changing the position at equal interval. So this is first, this is second, and this is third, right? If you observe the distance, then those 3 will be the same here. Okay, right? So then what is the advantage and what is the disadvantage for transposition of these conductors, right? So if you first see the advantage of transposition of conductors, when the conductors are transposed at regular intervals, the inductance and capacitance of the conductors will not be equal, right? So if the conductors are not transposed, right? So if the conductors are not transposed at the regular intervals, inductance, capacitance of the conductors is not equal. So but if you use the transposition, then inductance and capacitance will be equal. Okay. So the another advantage is that when the conductors are such that, so the telephonic lines are running in parallel with the transmission lines, so then there is a possibility of high voltages which are induced in the telephone lines, so which will result in noise in the telephonic lines, right? So but the transposition will greatly reduce this undesirable phenomena, right? So if you are not doing the transposition of conductors, in such a case, if the telephonic lines are running in parallel with the transmission line system, in such a case, in the telephonic line you will observe some noise due to the high voltage induced in the telephonic lines, right? So when you use the transposition of conductors, in such a case, you will not observe these voltages induced in the telephonic line, so that there will be no noise produced in the telephonic transmission, right? And in practice, the conductors are not transposed in the transmission line. The transposition is done in the switching stations and substations itself. Okay, so where this transposition will be in general, we do. So generally, we will do the transposition at the switching stations as well as substations. Okay, so these are the advantages of transposition of conductors. Right, first thing is inductance and capacitance will become equal. So when you transpose the conductors, and the second one is noise will not be developed when telephonic lines are running in parallel with the transmission lines, right? And this transposition generally will be done in the switching stations and substations. So then what is the disadvantage for transposition of conductor? So disadvantage, if you observe, literally there is no drawback with the transposition of conductors. So but there must be some care must be taken while marking the positions of your R, Y, B phases. So at the tower correctly, right? So while marking the phases sequence, right, R, Y, B phase sequence, so you must be very careful, right? So if incorrect marking, if you mark the this R, Y, B phase sequence incorrectly, so then the incorrect making of these will lead to the mismatching of phase sequence at the switching stations and what expected in the transmission line also, right? So the phase sequence will be different, right? When the phase sequence is different, so then what may happen? The induction motors, if they are connected to this mismatched phase sequence transposition, instead of rotating in clockwise rotation, they will rotate in anti-clockwise direction. So the process will be disturbed. Okay, so there you must maintain the same phase sequence, right? Otherwise, the equipment which are connected to those three phases will not work properly. Okay, this is the main disadvantage here, right? So there is no drawbacks, but while marking this phase sequence, you must be careful. So this is about the transposition of conductors, right? Now, if you observe the transposition of conductors in real time, so here three conductors. If you observe here, so at one end, right? Let it be sending end, let it be receiving end, right? Now here at this tower, we are transposing the conductor, right? So if you mark the letters here, so it is R phase, it is Y phase, it is B phase. Okay, so now this R phase is going to this next position, and Y phase is going to here, and B phase is going to here. Okay, so then after some more distance, again that position of conductors will be changing. Okay, so here in the three-phase system also it will be the same. Okay, this is also the three-phase system, so but it is for a low voltage. So in case of high voltage, you will generally use the towers like this, right? At a transposition tower, you will do the transposition of your conductors. Now let us determine the inductance of three-phase asymmetrical line with transposition, right? After transposition, if you determine the inductance of a asymmetric line, how the inductance value it will be. So let us see. Okay, so for this, consider a three-phase asymmetric line, so which is as shown in this figure here, right? In a three-phase asymmetric line, you will observe three conductors A, B, C, such that the distance between any two conductors is not same. Okay, so here the distance between A and B, we are calling it as D12, and distance between B and C, you are calling it as D23, and distance between A and C, we are calling it as D31. So these distances will not be same in a asymmetrical transmission line, right? And you also assume that there is no neutral wire in the transmission line system, so that if you take the sum of all the three phases, that value will be equal to 0. Sum of all the currents which are flowing in all the three phases will be equal to 0 if there is a no neutral wire. Okay, right? Here we are taking the transposition of conductors. So transposition of conductors is nothing but exchanging the position of conductor at a regular and equal intervals, right? Here we are exchanging at two positions, and the total transmission line length is divided into three sections here. Okay, so these are the positions of your conductors, right? In first section, conductor A is in position number 1. In the next section, it is going to position 2. In the next section, it is going to position number 3. Like that, other two phases also will change their position when they are going to second and third positions. Okay, so this is called the one complete transposition cycle. Okay, so this is called one complete transposition cycle, right? So when you use this transposition of conductors, so then this arrangement will cause each conductor to have the same average inductance over the transposition cycle, right? So if you observe the total this much distance, so then if you transpose the conductors at regular intervals, then the average inductance, so the average inductance will become same, right? So over the length of one transposition cycle, if you observe the flux linkages, right? So these flux linkages, and hence the net voltages induced in the nearby telephonic line will also be 0 here. Okay, right? So let us determine the flux linkages of your first section here, right? So three sections are there here. Okay, So now for the first section, if you determine the flux linkages of conductor A, okay, so which is represented with lambda A1, right? So lambda A1 here is nothing but flux linkages. Lambda is flux linkages. A here is of conductor A. 1 here is nothing but it represents the section number 1. Okay, so lambda A1 is the flux linkages of conductor A in section 1 here. Okay, so then so this value will be equal to 2 into 10 power minus 7. So into flux linkages of conductor A due to its own current, which is IA into ln 1 by RA dash. This will be the flux linkages of conductor A due to current flowing in conductor A itself, which is IA. Now, if you observe the flux linkage of conductor A, so due to current flowing in IB, that value is IB into ln 1 by distance between these two. So distance between these two is D12 here, right? So plus, so current flowing in the conductor C. So the flux linkage of conductor current flowing through the conductor C will be IC into ln 1 by distance between A and C, which is D13 or D31. Okay, so this is the flux linkage expression for conductor A in section 1, right? In similar way, you determine the flux linkage of conductor A here in section number 2. Okay, so then the flux linkage equation for conductor A in section number 2 will be lambda A2. So this value is equal to 2 into 10 power minus 7. So due to its own current, the flux linkages will be IA into ln 1 by RA dash plus, so due to current flowing in conductor B here, so this will be IB into ln 1 by, so this distance is the distance between A and B here. Now A and B distance here is D23, right? So distance between the position number 2 and 3 is the D23 here. Okay, so plus, so due to current flowing in conductor C, the flux linkage will be IC into ln the distance between A and C, so which is D12. Okay, this is the flux linkage of conductor A due to conductor A in section 2. Right, similarly, you determine the flux linkage of same conductor A in section 3 also. Right, so now in section 3, the conductor is occupying the position number 3 here. Right, so now due to current flowing in the section of conductor A itself, the flux linkage will be 2 into 10 power minus 7 into IA ln 1 by RA dash. Then plus, due to current flowing in the conductor B here will be IB into ln 1 by distance between A and B here. So which is D31 or D13 you can say. Okay, so plus current flowing to the conductor C. If you observe the flux linkages due to current flowing in the conductor C, then that value will be IC into ln 1 by distance between A and C. Here this in third section, distance between A and C is this distance, which is D23. Okay, so this is how you can develop the flux linkages equation for conductor A in each section. So due to current flowing in its own conductor as well as other conductors. Okay, so the lambda A1 is the flux linkage of conductor A in section number 1. So lambda A2 is the flux linkage of same conductor A in section number 2, and lambda A3 is the flux linkage of the same conductor A in section number 3. Okay, so now the average flux linkages will be sum of all these by 3. So if you find the average flux linkage of conductor A here, so that value will be lambda A is equal to lambda A1 plus lambda A2 plus lambda A3 by 3 here. Right, here you substitute all the values, lambda A1, lambda A2, lambda A3, all the values from these equations. Okay, so then we are going to sum all these, right? In all the cases, 2 into 10 power minus 7. So this will be the common. Okay, then here if you observe the first term, so IA is common here. So if you take it IA 1 ln 1 by RE dash. So first term is, so 3 times IA ln 1 by RA dash you will get. Okay, so here I'm writing here 2 into 10 power minus 7. So 3 IA ln 1 by R A dash you will get. Okay. Then plus. So then if you observe here, if you take IB is common in the second term, so then IB from here, IB into ln 1 by D12 plus 1 by D23 plus ln 1 by D13 you will get. Okay, this can be written as IB into ln 1 by D12 D23 D31. Okay, so if you sum all these, you will get IB into ln 1 by D12 D23 D31. So that you can write here, right? IB into ln 1 by D12 D23 D31 plus. So then if you take these terms, right, here IC is common. IC is common. If you take it out, then you will be having ln 1 by D31 plus ln 1 by D12 plus ln 1 by D23. Okay, if you write this IC ln 1 by D12 D23 D31 again you will get, right? So the last term will be IC into ln 1 by D12 D23 D31. So this is the sum of all these. Whole divided by 3 you have to take, right? Now if you distribute this 3 here, so for this section you will get 3 will get cancelled, so that 2 into 10 power minus 7 into, so this when 3 gets cancelled, IA ln 1 by RA dash you will get, right? So here you will get 1 by 3, here you will get 1 by 3. Now this 1 by 3 if you take to the power of this, so then you will get the second term as this equation, IB into ln 1 by D12 D23 D31 whole to the power of 1 by 3 plus IC ln 1 by D12 D23 D31 whole to the power of 1 by 3 here. Okay, right? So now here if you observe this expression, so here this term and this term you have the common, you take it outside, right? So that the equation of lambda A will be equal to 2 into 10 power minus 7 into IA into ln 1 by RA dash plus, when you take this term as common, then you will get plus IB plus IC into ln 1 by D12 D23 D31 whole to the power of 1 by 3. So now as you know, so when there is no neutral, then IA plus IB plus IC, sum of all the currents in all the 3 phases will be equal to 0. Now from this expression you can take IB plus IC will be equal to minus IA. So here in place of IB plus IC you can take minus IA. Okay, then the flux linkages expression lambda A will be equal to 2 into 10 power minus 7 IA into ln 1 by RA dash minus IA into ln 1 by D12 D23 D31 whole to the power of 1 by 3 you will get. Right, here you have IA as common, you take it outside. Okay, and at the same time, so instead of this power 1 by 3, so right here minus ln 1 by some value x, this can be written as plus ln x. Okay, so like this we are writing, right? Minus of this entire term we are going to write it as plus of this term. Okay, so lambda A is equal to 2 into 10 power minus 7 IA into ln 1 by RA dash plus IA into ln D12 D23 D31 whole to the power of 1 by 3 you will get, right? If you take IA common, so then the lambda A expression will be equal to 2 into 10 power minus 7 IA ln 1 by RA dash plus ln ln D12 D23 D31 whole to the power of 1 by 3 you will get. Okay, so this will be looking like log A plus log B, so which is log AB. So then the flux linkages of conductor A, so will be lambda A, so which will be equal to 2 into 10 power minus 7 IA ln D12, D23, D31 whole to the power of 1 by 3 by RA dash you will get. Okay. So this is the flux linkages expression for conductor A. Okay. So here this D12, D23, D31 whole to the power of 1 by 3 you can call it as D equivalent. So which is called the equivalent equilateral spacing. Okay. So equivalent equilateral spacing. Then so this equation you can write it as lambda A is equal to 2 into 10 power minus 7 ln D equivalent by R A dash you will get. Okay. So this is the flux linkages equation. Right. Now once you know the flux linkages, then you can determine the inductance. Right. So the inductance of conductor A or phase A, LA is equal to, so here you will get IA. So this lambda A by IA here. So flux linkage is lambda A by current IA. Now from this expression, lambda A by this IA will be equal to 2 into 10 power minus 7 ln D equivalent by R A dash you will get. Okay. So the inductance value of phase A will be equal to 2 into 10 power minus 7 ln R equivalent by R A dash. Okay. So this even can be written as 2 into 10 power minus 7 ln dm by ds. Here dm is the mutual GMD and ds is the self GMD. Right. So the mutual dm will be equal to D equivalent. So whose value will be equal to D12, D23, D31 whole to the power of 1 by 3. Right. And ds is equal to R A dash, which is nothing but 0.7788 times the R A, radius of conductor A. Okay. So now if the RA, RB and RC, so radius of conductor A, radius of conductor B and radius of conductor C. So if all the radius of all the conductors are same, so then the value of inductance for each conductor also the same. So LA is equal to LB is equal to LC. Okay. So like this, when you have the transposition of conductors, the inductance in each phase will be same. So before transposition, if you observe the inductance of three-phase asymmetrical line, if you observe, so that those values are not same and also they are complex numbers. Okay. So to get the same value of inductance for each phase, here you do the transposition so that you will get the balanced receiving end voltage at all the time. Okay. This is how you can determine the inductance of a three-phase asymmetrical line by using transposition. So let us see one numerical problem here so that you can understand better. So here the problem is the three-phase conductors, right? So the three conductors of a three-phase transmission line are arranged at the corners of a triangle whose sides are 2 meters, 2.5 meters and 4.5 meters. Calculate the inductance per kilometer of the line when the conductors are regularly transposed. So the diameter of each conductor is 1.24 centimeters. Right? Here they are saying that you have a three-phase transmission line with the three conductors, and the three conductors are arranged at the corners of a triangle. Right? So on the distance or sides, if you observe, so one side is 2 meters, another one is 2.5 meters, another one is 4.5 meters. So that means, so like this, the conductors are placed here: conductor A, conductor B, and conductor C. Right? So this is 4.5 meters one side, other side is 2 meters, other side is 2.5 meters, like this. Right? Or simply you can say that these are D1, D2, D3. Okay. So D1 is equal to 2 meters, D2 is equal to 2.5 meters, D3 is equal to 4.5 meters. Right? Here these are nothing but in our equation you can say D12, D23, D31 also. Okay. Instead of saying D12, D23, D31, I am calling them as a D1, D2 and D3. Okay. And radius of each conductor is RA, RB and RC. Okay. So now here they are given that diameter of each conductor is 1.24 centimeter. So the radius of each conductor also will be the same. So which will be equal to 1.24 by 2. So centimeters. So you are getting the radius of each conductor. So whose value is R equal to 1.24 by 2. So the value you are getting it to be 0.62 centimeters. Okay. So now you have to determine the inductance here. So the inductance equation per phase per meter length will be 2 into 10 power minus 7 ln dm by ds. Here mutual GMD dm will be equal to d equivalent, which is equal to d1 d2 d3 whole to the power of 1 by 3. Okay, d1 d2 d3 whole to the power of 1 by 3. So the distances, all distances you already know. So d1 is 2, d2 is 2.5, d3 is 4.5. Simply substitute those values here in this equation, then you will get the value of dm. Okay, so then ds is nothing but it is a self GMD. This value will be equal to r dash for each conductor, right? So this value is equal to 0.7788 times the value of r. Okay, so the radius of conductor is 0.62 centimeters. Now if you substitute this value here, you will get the value of ds. Okay, so now you have to use ds is equal to 0.7788 times r and dm is equal to d1 d2 d3 whole to the power of 1 by 3. So these two expressions for calculating the dm and ds in this expression, right? So this is the value of inductance in henries per meter. Okay, right. So now, so the dm value what you are getting here is 282 centimeters, right? And the value of ds, how much you are getting? So the value of ds here is 0.7788 times the r value, and 0.7788 multiplied with r here is 0.62. If you do calculate with the calculator, so that you will get the value of ds. So how much you are getting? So once you if you multiply 0.7788 with the 0.62, so then you may be getting 0.4829. Okay, so this is in centimeters. So this value is in centimeters. So this is also in centimeter. So the inductance L of each conductor will be the same. Why? Because the radius is same here. So that value is 2 into 10 power minus 7 ln dm by ds. Okay, so this value is in henries per meter. Okay, so L is equal to 2 into 10 power minus 7 ln dm here is 282 and ds is 0.4829. So this is in henries per meter, right? Once you calculate this value, you are getting 12.74 into 10 to the power of minus 7 henries per meter length. Okay, so 12.74 into 10 power minus 7 is the value of inductance for each phase per meter. So but here in the problem they are asking the inductance per kilometer, so not for 1 meter. So to get the value of inductance per kilometer, simply you have to multiply this with 1000, so that the value of inductance will be in henries per kilometer, right? So then that value will be 1.274 into 10 to the power of minus 3. You will get in henries per kilometer. So this value even you can write it as 1.274 millihenries per kilometer. So this is how you can determine the inductance of a three-phase asymmetrical line. So when the conductors are transposed. Okay, right. So thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.